look at the synthesis of alcohols. There are different ways of preparing alcohols, and we want to discuss them in details. We are saying the first one, alcohols can come from alkenes. When you have alkenes, you can hydrolyze them in the acetic medium to form secondary alcohols. For example, if you have RCH, double bond CH2, this one you can hydrolyze in presence of what? In presence of water. And then you do what? You heat. No, you don't have to heat here. You don't have to heat. Yes, when you are hydrolyzing, for example, the cyanide, you need reflux. But when you are hydrolyzing the alkenes, these are reactions that are spontaneous. They don't require any energy. So by Markovnikov's rule, this hydrogen comes here, then the OH from water comes here, leading to the formation of a secondary alcohol. So basically, this is what happens. And under the mechanism, we have already looked at these reactions, but I can just summarize the mechanism very fast, whereby we have RCH double bond CH2 being attacked by these hydrogen ions, probably from a sulfuric acid. So the double bond attacks that hydrogen, and by Markovnikov's rule, it will be attached to the carbon with more hydrogen atoms across the double bonds. So it becomes CH3. This one, which has lost the double bonds, will become positively charged. And because it has become a carbocation, the OH2 has oxygen that has one pair of electrons that attack. When you attack, what happens? You form RCH, then CH3, OH2. So oxygen becomes positive. When oxygen becomes positive, the oxygen becomes positive because, first of all, it has created an extra bond, and therefore it has used one of its lone pair of electrons, getting that positive charge. And therefore, to neutralize the positive charge, one of the hydrogen atoms breaks off as a hydrogen ion on the OH2, leading to the formation of RCHOH, then CH3, OHCH3. So this is a secondary alcohol that has been formed. I hope we are together at this level. An example, as long as the R has been replaced by any alkyl group, maybe CH3, CH2, you can follow that same mechanism and you have what? The answer. You have the answer there. Now, also, in some cases still here, they might give you concentrated sulfuric acid on these hydrogen ions. When you have concentrated sulfuric acid, then you will end up forming a sulfonic acid, a sulfonic compound. I want to show you how that happens. So, if for example, we were given here conc sulfuric acid, if this is concentrated sulfuric acid in presence of what? Of water. So what happens here is that I want to show you what happens in the mechanism. The sulfuric acid will dissociate first. Remember, when it is conc, it is a weak acid, leading to the formation of hydrogen ions and the hydrogen sulfate ion. So what happens is that you have RCH double bonds, CH2, attacking the H plus, leading to the formation of a carbocation, RCH, then positive, then CH3, CH3. Now this carbocation, before it is attacked by water, it can be also attacked by this hydrogen sulfate. Hydrogen sulfate is also a nucleophile. Is also a nucleophile, thereby the oxygen has lone pairs of electrons. It uses them to attack that carbocation, leading to the formation of RCH, O, SO3H, then CH3, CH3. So this hydrogen sulfate branch, can be removed or can be substituted by the water molecule. So what happens is you have your H2O, and then you have RCH, CH3, then O, SO3H. What happens is that this oxygen has one pair of electrons, so it uses them to attack that carbon, and then it forces this bond to break off. When it forces that bond to break off, still you are going to form RCH, CH3, then OH2 plus. OH2 plus. And then here we can lose hydrogen, leading to the formation of RCH, CH3, OH. RCH, CH3, OH. So that's exactly what happens. That is what happens. So in the first reaction, if they have not specified, they are just saying H plus in presence of the water, you don't need to show the formation of the hydrogen sulfate. However, in this case, since they have insisted that we use concentrated sulfuric acid, in some textbooks, you will see the formation of this kind of a compound. So when you see it, you should not be what? You should not be confused. When you see that kind of compound, you shouldn't be confused. However, it is an intermediate that is quickly replaced by a secondary alcohol, where the hydrogen sulfate is replaced by the OH. So that is our first reaction. Our first reaction leading to the formation of alcohol, but specifically secondary alcohols. Now let's look at our second reaction that leads to formation of alcohols. It is from alkyl halides. These are nucleophilic substitution reactions. You have seen them in the reactivity of alkyl halides, whereby we say that if you have a solution of sodium hydroxide in presence of heat, you can change an alkyl halide into an alcohol. Generally, this is what we are saying. We are saying that if you have R, then X in presence of sodium hydroxide, and heat, this sodium hydroxide should be aqueous. That's what I'm saying, heated with a solution of sodium hydroxide. It should be a solution. If you do not show any state there, then it means you have insisted that it is a solid, and solid sodium hydroxide does not react with alkyl halides in that way. So in this case, the OH replaces the what? The X, leading to the formation of ROH. Of course, the byproduct will be sodium what? Sodium X. This sodium going along with the halides. And we say these are substitution nucleophilic reactions. And remember what we said, that they can be classified into unimolecular or bimolecular, depending on the class of the alkyl halide. Depending on the class of the alkyl halide. We say if the alkyl halide is primary and secondary, these two undergo a nucleophilic substitution bimolecular reactions, where the activated complex has two species, one being attacking and the other one breaking away. And then we say if it is a tertiary alkyl halide, this one will undergo nucleophilic substitution, unimolecular reaction. And if you want to refer to this kind of reactivity, please go back and check our notes. So an example here can be probably CH3, CH2, CF in presence of sodium hydroxide, aqueous, and heat. This one will change directly to CH3, CH2, or H. So the class of the alkyl halide determines the class of the alcohol that shall be formed. The class of the alkyl halide determines the class of the alcohol to be formed. If the alkyl halide is primary, the alcohol will be primary. If the alkyl halide is secondary or tertiary, even the alcohol being formed shall be the same. Next we have from carbonyl compounds. We can prepare alcohols from carbonyl compounds. Remember, carbonyl compounds have a general functional group of carbon, oxygen, double bonds. These are carbonyl compounds. This is their functional group. Carbon, oxygen, double bond. So what happens is this bond can be reduced by addition of hydrogen, because you remember from our definition of reduction, reaction is in O level, reduction can be addition of hydrogen. So the moment I add hydrogen, I use one of these bonds, these double bonds, to create a bond between oxygen and hydrogen. I have successfully converted a carbonyl compound into a ketone. And we are going to say that we have, in organic chemistry, we have many reducing agents. But the most common one is called lithium aluminium tetrahydride. And this one reduces, if you have aldehydes, they will be reduced to primary alcohols. Aldehydes are reduced to primary alcohols. And ketones, we are going to say ketones are reduced from secondary and are reduced to secondary alcohol. What do I mean here? I mean, of course, this is an aldehyde. An aldehyde has general formula RCOH. And then a ketone has a general formula RC, double bond O, then R prime. So what happens is that these compounds, this one here, when it is reduced, it's going to be reduced to what? To a secondary alcohol. Of course, you can see. This one will be reduced to a secondary alcohol. Why? Because this carbon with the functional group already has two alkyl groups. So it means the secondary alcohol we shall have is RCOH, then H, R. Secondary. However, here, since this carbon with the functional group has only one alkyl group, this one shall be reduced to a primary alcohol, CH2OH. So that's what we are saying. It means you cannot reduce carbonyl compounds. You cannot be reduced to tertiary alcohols. They cannot be reduced to tertiary alcohols. So we are saying aldehydes are reduced to primary alcohols. Ketones are reduced to secondary alcohols. And I've said the most common reducing agent is lithium aluminium tetrahydride. This reducing agent works in presence of dry ether. It works in presence of dry ether. So let's look at an example. Generally, for ketones, for aldehydes, it will be RCHO, whereby when I write it like this one is the same as this. This and that, they are the same. So if I use lithium aluminium tetrahydride, that should be in presence of dry what? Dry ether. If that happens, what do I form? I form RCH2OH. I have eliminated the carbon oxygen double bond. You say this like this. I have eliminated it, but I have also increased the number of hydrogen atoms. I have added 2 of them. So what happens here is that in reduction, the number of oxygen hydrogen atoms have increased, and also we have eliminated the carbon oxygen double bonds from the compound. So this is a primary outcome. So R can be, if R is CH3, so that would be CH3, CHO. If you have lithium aluminium tetrahydride in presence of dry ether, so it will become CH3, CH2OH, OH. Ether, if it was CH3, then CH2, or CHO, then it means this one will still be CH3, CH2, CH2 again, OH. So even the number of carbon atoms does not change. We are just changing the functional group from an aldehyde to an alkyl. This is a reduction reaction, right? Then also, if we want to produce secondary alkyl halides, this one here we are producing primary alkyl halides from aldehydes, secondary alkyl halides from ketones. I'm going to have R, then C double bond O, then R prime. The R and R prime can be the same, it can be different. But this is the general formula of the ketone, right? Still, I am using lithium aluminium tetrahydride in place of dry ether. So what happens is this functional group is going to change to COH. So it becomes RCOH, then HR prime. So for both cases, we are increasing the number of hydrogen atoms by 2. A clear example, if R is CH3, that will go on the O, then R prime is CH2CH3. Then we are adding lithium aluminium tetrahydride in place of dry ether. So what will we form? This carbon oxygen double bond is going to change to the carbon oxygen bond, leading to the formation of CH3C OH, then CH2, CH3. So you see that here we have formed a secondary alkyl, a secondary alcohol, because the carbon with the OH has two alkyl groups, or is bonded to 2 carbon atoms. So reduction reactions can also always lead to the formation of alcohols. The fourth way of producing alcohols, we had already looked at it. When we are looking at the reactivity of aldehydes with Grignard reagents, we are looking at the fourth, which is the reactivity of Grignard reagents still with grignard reagents with carbonyl compounds. Are we together? Still here, this helps us to form a tertiary alkyl halide from a ketone. I mean a tertiary alcohol from a ketone. This reaction is almost the same as this, right? However, this one here, the one we were discussing from carbonyl compounds, this was a reduction reaction. This was a reduction reaction. But now this one is not a reduction reaction, it's actually a reaction with grignard reagents. And in most cases, this always leads to the increase in the number of carbonic atoms. A clear example, if I want to form a primary alcohol, you will allow me to use this space here. If I want to form a primary alcohol, I'm going to use a grignard reagent. So in this case, I can use this, then MgBr. That is my grignard reagent that I'm using. R can be anything. How we said here, we have to use methanol. If you want a grignard reagent to change into a primary alcohol, then the carbonyl compound we're going to use is methanol. What is methanol? Whereby we say this carbon oxygen bond will come and punch itself here, losing the double bond, leading to the formation of course, this will be in presence of dry what? Dry ether. Be in presence of dry ether, then we form RCH2. Then this one has now come as what? C, then O. I can write the O here, but this C has two hydrogen atoms. One here, and then another here. Now this O establishes the bond with MgBr. And we say this one on hydrolysis. On hydrolysis, in this case, I can use H plus in presence of H2O. However, somebody can say, somebody can use dilute HCl. Any that you use, it will work. And then that one will say, the MgBr is replaced by hydrogen, leading to the formation of RCH2, then CH2, or what? OH. CH2OH. This one here is a primary alcohol. We say if you want to form this, we are forming a primary alcohol. If you want to form a secondary alcohol, you can use still the same grignard reagent. If I use the same grignard reagent, it will allow me. But now I am going to change. Instead of methanol, I'm going to use higher aldehyde. That's what it says. Other hydrides react to form secondary alcohols. So in this case, I can use maybe R prime, then C double bond or H. That's what I'm reacting with now. So what happens is that this one is going to react in presence of dry what? Dry ether. This one is going to react in presence of dry ether. What do we form? We say the carbon oxygen double bond. The carbon oxygen double bond will come and punch itself between carbon and magnesium, losing its double bond, leading to the formation of what? So it's going to be RCH2. So from CH2, now I add C. Now it's going to be C, but this carbon has hydrogen down, right? I can put it down. Then it has another R prime. So that R prime, I'm going to put it here, R prime. Then it has carbon oxygen double bond, which I'm saying it becomes a single bond now. And then the magnesium attaches itself there. Magnesium bromide. And this one on hydrolysis. This one on hydrolysis, that is in presence of, we are going to use dilute HCl. You said what we form? We form R, then CH2. Where we have the MgBr is going to be replaced by OH, by H I mean. So it becomes RCH2, CH, R prime, then OH. So this reaction has led to formation of a secondary alcohol. We have formed a secondary alcohol. Why? Because the carbon with the functional group has two alkyl groups attached to. So that is the secondary alcohol. Let's look at the tertiary alcohol. If we want to form a tertiary alcohol from this very pregnant reagent, what do we use? We say here, you must use a ketone. You must use a what? That's what I'm saying. Ketones react to form tertiary alcohol. So we are going to have formation of the tertiary alcohol. Let me write it here. So we are going to still use the same pregnant reagent, RCH2, MgBr, RCH2 MgBr. So I'm going to use the ketone now. Plus, I can use the ketone R prime, C double bond O, then R double prime. But still remember, pregnant reagents react in presence of dry ether. So if I say in presence of dry ether, what do I form? In presence of dry ether, what do I form? This carbon oxygen double bond, remember, it comes and punches itself here using its double bond. So we are going to have R CH2, then this carbon which has oxygen and R prime, so we have R prime here and R double prime here. Then this oxygen is going to attach itself to the magnesium bromide is going to attach itself on the oxygen. Now this one, if we do hydrolysis, the MgBr will be replaced by hydrogen, right? But now this hydrolysis must not be in the acidic medium. Why do we say it shouldn't be in the acidic medium? Because there is a possibility that the secondary alkyl halide can be dehydrated by the acid input, leading to the formation of an alkene. So what we need now here, we are going to use ammonium chloride, right? So we are going to say we are hydrolyzing in presence of ammonium chloride. That will lead to the formation of CH2, then C, R prime, then OH, then down R prime. So that's what we have right here. And the reason why we acknowledge or we require that students do not hydrolyze the tertiary alcohol in this sense is because the alkyl groups, these alkyl groups have what we call positive inductive effects. Positive inductive effect is the tendency to push electrons towards the what? To push electrons towards the carbon with the functional group. When you look at this, for example, there is R prime here, then there is R double prime. So you are looking at this R pushing electrons towards the carbon with the OH. Even this one pushing the electrons towards this carbon. Even this main alkyl group, RCH2, is also pushing electrons towards this carbon. Now this electron C, because the carbon-oxygen bond is polar, slightly polar, and oxygen is more electronegative, it means these electrons are going to be further pulled towards the OH. So the OH site shall have a lot of electrons, and therefore this is susceptible to electrophilic attack more than the primary and the secondary alcohols. That is why it is not advisable to use what? To use a dilute HCl here. If you use ammonium chloride, it will be much better. It will be much better. But still, even if you don't use ammonium chloride and you have used an acid, you might get the product if you have regulated the acid. But if you have not, you might end up getting a mixture of compounds where you have an alkene and then you also have tertiary alcohol. So when you find some books that have not added ammonium chloride, do not say the teacher told us it's supposed to be like that, but we have formed something different. No, it can always work also.